Oh man, I think specific impulse is going to take us a long time to discuss, isn't it?
Trust me, John, it's only a matter of seconds.
Ugh. Hey y'all, it's Dr. Know-It-All. Guess what? I'm back with Dr. Scott Walter again. What a surprise, because we're coming in, we're recording the last two videos together. So, it's just a marathon for us. Anyway, welcome back, Scott. What are we going to talk about today?
We are going to talk about specific impulse.
Or just to make it more confusing, it's ISP.
ISP, or some people would say impulse specific.
Yes.
And
those French, they always get the letters backwards.
Yep. Yes. So it's definitely specific impulse is how most people talk about it. And we want to discuss this because there's a lot of confusion about what it really is and the understanding. So everyone knows it's something to do with the efficiency of a rocket engine, but nobody really quite understands what it means. And I've been meaning for a long time to be able to get this out there to help get through the confusion, because there's even a lot of creators that I would say maybe don't quite grasp it enough, or don't grasp it enough to be able to explain it to anyone else.
Right.
And I actually put together a script for Ellie a few months ago that she made into a short. And believe it or not, my script was only 90 seconds on the read through, but she had to cut it down to 60. Right. That explains what's going on. But then again, it missed some of the nuance. And as you know, you and I are pretty good at filling it.
Right.
So here we go. So,
okay,
John.
So where do we want to start with the
units?
Big picture? Big picture.
Right. What are the units of specific impulse? What are the units?
Well, we were talking about this offline, and I think the most confusing thing to people, including me, is that the units
the man on the street
goes by are seconds. Yeah.
Seconds, right.
But that's very confusing.
Weird. It's like,
right.
It's efficiency is in seconds. So sometimes we're used to measuring things in time that maybe shouldn't be measured in time. Like, how far is it to Atlanta, John, from your house?
Well, yeah, I'd say like an hour usually, something like that.
Yeah, an hour. But, when I say how far, I'm thinking you're going to tell me what the distance is. But a lot of times we're used to thinking of how long it would take to go there using a specific mode of transportation.
Right.
But there are other times where it doesn't make sense to use something in a matter of seconds. It has absolutely no meaning. So if a light bulb goes out in my house and I say, John, can you go get me the 10-second light bulb? You'd be like, the what? And, is that the light bulb that burns out after 10 seconds? I'm like, no, that's the one that with the 10-second power rating. You would say that makes no sense. Yeah. So light bulbs are rated in watts for a reason. So why aren't rocket engines, when we're talking about efficiency, why aren't they rated in something that makes sense, like miles per gallon? Everyone understands miles per gallon when it comes to a car.
Right.
You don't have to explain it to anyone. It's almost an obvious kind of description.
Right.
And those are the best ones. The ones that you don't like, a good joke, you shouldn't have to explain it.
Right.
So why is it in seconds? Because it's a matter of seconds, remember?
Yes. And if you didn't get the cold open at the beginning, now you get it. You're gonna groan.
Right. And now you're going to know why it really isn't seconds. And that's because the units are not in seconds.
Mm-hmm.
So let me go ahead and get myself there. These are the actual units.
Right.
Now, these are the units in the SI system. This is newtons over newtons per second.
Right.
And if you want imperial units, it would be like pounds over pounds per second.
Right. And so just to keep that, and just to let people know. So if you're in America and you're like, I don't know what a newton is, it's a pound is identical because they cancel out. So you can do this either way. So if you want to imagine pounds per second, that's totally fine. So yeah.
Now, if you remember from algebra classes, like variables that you can kind of cancel out if one's in the numerator and the other one's in the denominator. Right. And so with units, and this is something a lot of people weren't taught in grade school, is that you can also do the same thing with units. Right. Is that if you get one unit over another unit, they can kind of cancel out. And so when that happens, the ends, we cancel out or put a line through it, and you basically get a 1 over seconds. Well, this is the reciprocal of a reciprocal, which means you end up in seconds.
Yeah.
So
because you can imagine multiplying the top and the bottom by S, and the bottom will cancel, the S's will cancel, and you'll end up with an S.
Yes. Yeah, you do all that thing. But in the end, boom, it's seconds. So there's two things we want to look at is first, why was the original description newtons over newtons per second in the first place? And second, is there any intuitive feeling or meaning to these seconds that we can apply? Because a lot of times the best way to understand something is to have a feel for the unit. And most people, when I say that the RAPTOR engine has an ISP of, what is it, like 360 or something like that, seconds, it's like, great. But what does it really mean? I know what 100-watt light bulb means. I know what 100 meters means, but to me, the idea of an efficiency, I know how long 300 seconds is, but I can't relate that to the idea of a rocket engine. And we're going to get into that.
Right.
So this is basically how ISP is defined. It's the engine thrust divided by the propellant consumption rate. And propellant is fuel plus oxidizer put together. Right. Okay. Whenever you see something that has a rate in it, that usually means it's something divided by time.
Right.
So when we talk about, how fast someone is walking, their walking speed, it might be like feet per second. If we're talking about the number of parts that a factory is producing, it might be parts per hour or something like that. So whenever there's a rate, there's something divided by time. So you can suspect that there's going to be something divided by time here. And then consumption is measurement of something, how much of something we have.
Right.
And in physics and engineering, there's usually two ways that we measure quantities. And what are those, John?
Well,
typically.
Well, I know in this case, there's usually either mass or weight.
Or volumetrically. So either we say like, gallons per second or something like that would be like a flow rate. Or, we might say, kilograms per second or something like that. So typically it's either volumetric or it's going to be mass.
Right.
When we do it volumetric, it's because the volume of the thing that we are measuring tends to not change. Right. So gasoline is measured in gallons when we are putting in our tank because the volume of it doesn't change. It does. Okay. With pressure and temperature. All right.
But not by a lot.
Not by a lot. However, when we buy propane, we buy it as, in pounds of propane gas, not gallons of propane gas, because it's this fluid that's compressible and everything else.
Right.
So usually the most invariant way to measure the quantity of anything is mass, because mass is invariant. So you and I have the same mass on Earth as we do on Mars, as we do on the moon. Right. However, our weight is different in all those different places because weight is your mass times whatever the local gravitational acceleration is. All right. So normally,
and this is, I'm going to get back to this. I'm going to get back to this in a second, but continue your explanation.
We take gravity completely out of it and say, look, just focus on the mass, because that's the thing that's invariant. And you would think when it came to rocket science, where you're going to these different planetary bodies with different gravity, it's like you'd want to get gravity completely out of the whole thing. Nope, not this time. So basically, it's going to be, ISP is going to be thrust over propellant weight. That's what they mean by consumption, not propellant mass. So it's not a mass flow rate, which rolls off the tongue. It's a weight flow rate.
It's also not a volumetric flow rate either. It's not gallons per second either.
Right.
So yeah.
And it's hard for me to say weight flow rate because it's just not something we come across. It just seems like a really strange concept to me because in fluid mechanics, it's always mass flow rate. Always.
Well, and the reason why, of course, is that thrust is also measured in the same units as weight.
Right. So what ends up happening is that thrust is measured in newtons. And then you have your mass flow rate, which is going to be kilograms per second, but they sneak this gravity in there to convert that then over, because you can put that in there. Whenever you have kilograms times an acceleration g, that basically turns it into a unit of newtons.
Right. And g in this case, of course, would be meters per second squared in this case. So, and kilograms meters per second squared is a newton.
And everything is out. Now the question is, if they didn't sneak the gravity in there, and remember, gravity, g depends upon the planetary body you're on. So this is the gravitational acceleration on the surface of Earth, not on the moon or Mars or in Leo or in Geo or anything else. It's at the surface. So if you take that out, you will end up having, your ISP would actually end up being in units of meters per second velocity.
Right.
Which is basically another way that you look at the rocket equation. There's two forms of the rocket equation. One that uses what's called effective exhaust velocity.
Right.
And the other is using ISP, where ISP is multiplied by G sub C, where G sub C is gravitational constant on the surface of Earth, to convert it into effective exhaust velocity.
Right.
So they're basically one the same thing.
Yeah.
And that's why ISP is what it is. But now the question is, what does it mean?
Right.
Okay. And this is where we wanted to kind of shift over to the, we talked about earlier about the single stage to orbit. So now,
and if you haven't caught that video, definitely check out that video. It'll be up there.
Right.
So
now,
a couple of things about units here. The first thing is that's really confusing is if you had a rocket test stand on the top of Mount Everest, your ISP would be very slightly different than it is at sea level. So because the gravitational force is a little bit less on the top of Mount Everest than
if you were to be measuring it there, exactly.
Yes, exactly. So this is what's so bizarre about this.
It'll also be different because of the fact you're more in a vacuum than
well, there's that. Yeah, okay. But I'm just assuming the same pressure. But anyway, it's a very thing because it's a weird thing because weight is not invariant. That's the thing that's weird. Weight depends on where you are. Mass does not. So something, if you don't know this, and one of the reasons I hate imperial measurements so much is that, but in this case, it actually goes in the favor of imperial measurements, is on Earth, when you say I weigh 180 pounds, that actually is accurate. That's the weight that you have. That is your mass, which I believe is measured in slugs in imperial, times the force of gravity, which is 32 meters per second in imperial units. Whereas kilograms is not weight, it's actually mass. People say mass. I weigh 70
use it
kilos,
the wrong way.
But you don't. You actually
we should be saying how many newtons do you weigh, not how many kilograms.
Yeah.
But what we're doing is we're using the newtons to tell you what your mass is. So you should. So yes, the doctor, if he tells you you weigh that, you should correct him. Say, no, that's my mass.
Exactly. You should say, because basically the really rough rule of thumb is just multiply by 10. So if you weighed 70 kilos, you actually weigh 700 newtons approximately. So but nobody understands that unit, not even people who speak SI. Nobody's like, I weigh 700.
Exactly. Now if you go back to the definition that we have there again, so a lot of rocket scientists, when you ask them what ISP is, they will say it's the amount of propellant that you need to consume per second per unit of thrust. So they put it in this really wordy way that's hard to understand. It's like, what do you mean? It's like, well, if I want to produce a certain amount of thrust, that's how much propellant I need to consume per second to be able to maintain that thrust. Oh, okay. But can you still put it in terms that I can understand? It's like, yes, very easily. The reason why you have a Raptor engine, which I think is like 363 seconds, is that is the amount of time it will take a Raptor engine at its rated thrust to consume an amount of propellant equal to the thrust.
Right.
So it is able to consume, or it's able to produce, I think, something like 260 metric tons of thrust.
Right.
That's what it is, which means in order to consume that amount of propellant, 263 metric tons of propellant will take it 363 seconds.
Right.
That's what the seconds means. It's the amount of time to consume a thrust worth of propellant. Now, how can you turn that into another way? Well, if we take our rocket and turn around, I know you've got kind of an animation for that, but basically, if I have a rocket sitting on the stand and it has a total mass, and let's just say the mass is all propellant because I have a magic rocket where everything else has no mass.
Right.
So the only thing is propellant.
I love physics. We have round cows, spherical cows, and massless rockets.
Right. And it weighs 1 million. Choose your units, 1 million newtons or 1 million pounds. Okay. And my rocket can produce 1 million pounds or newtons of thrust. So they're exactly equal. And because they're exactly equal, it means I have just enough thrust to make that thing come off the ground when I light it up. So the thrust and the weight exactly equal, and it can go up. And that means if I continue at maximum thrust the whole time, not worrying about max Q and all this other stuff, but just going on up, I am going to run out of fuel after the ISP of that rocket. So if the ISP is 300, within 300 seconds, it'll use it all up. So does that mean a rocket engine can only burn for 300 seconds if that's its ISP? It's like, no. No, actually, we could build the rocket and it could have 1.5 million pounds of propellant there, but only 1 million pounds of thrust. And what's going to happen? It's going to sit there for 150 seconds until it burns off 500,000 pounds of propellant for no reason except the fact that you have all this concrete you want to get rid of. Right?
Yes, and SpaceX is quite good at that, apparently.
Yes, evidently. Zach Olin had a great tweet about that. That was really funny, showing this thing that was like removing concrete from roads. And he says, I know a faster way. You have to look at it. It's funny. But So you could do that. And then that means that once you get down to 1 million pounds, then you could finally take off and you will be able to go up for 300 seconds.
Right.
So roughly.
Or the other alternative, of course, is to throw a second engine on there with the same ISP and burn the fuel, and then you get double the thrust. So
right. Then you get double that. But the whole idea is you want to kind of match them out. So, so if you know the overall ISP of the first stage in the mass and everything else is roughly, you can use it as a rule of thumb. That's about when MECO is going to happen. Okay. Right. So if you have an engine that only has like 250, expect MECO to be somewhere around there. And if it's got something more like 400, it's going to be a little bit longer. Now, it's a rule of thumb for a couple reasons. One is that for a real rocket on the first stage, maybe 70% of the mass of the rocket might be in the first stage.
Right.
You know, because you get a second stage and everything else, which means you only get 70% of that million. So it's like, oh, it's only going to be 70% of that ISP. So that means it's going to be a little bit shorter. Okay, there's there. But then there's the other thing is that once you start getting up and the rocket starts getting a little bit lighter, you don't need to be maximum thrust anymore. So you might throttle back, which means you're not consuming the fuel quite as much, which means you can get a little bit of it more back. So it's, again, it's a rule of thumb for a reason.
Right.
And the other thing we've also discovered is that what happens when you get higher up in altitude?
Well, I mean, there's less gravity too.
Yeah, your weight actually goes down, not just because you're getting rid of the mass, but it's actually getting lighter because of gravitational loading. And what is the acceleration of gravity in low Earth orbit?
You told me, I know it's 9.8 meters per second squared on Earth, but it's a small fraction. Isn't it like 2 or something?
No, it's low Earth orbit. So low Earth orbit, it's about 7 meters per second.
7, yeah.
So,
but I mean,
it's about 70% of what it is on the surface.
Yes, about 2 meters per second squared less.
Right.
Yeah, but anyway, but it is a lot less.
Right.
Because you're getting out of that gravity well.
Right. In a geo, it's like 0.2 meters. It's like almost zero up there. Right. So what ends up happening is this whole idea of ISP when you're in gravity-free space starts to get a bit silly because it kind of loses that meaning of like, well, that's how long I can run my rocket, right? It's like, well, you take a rocket engine with the same ISP and you put it on the surface of the moon and you can load 6 times more propellant. So it means it's going to run 6 times more technically for the same ISP that you have in there. So it is a little bit tricky on how you do the comparison, deciding it. But that is the rough feel.
But that's also the reason why weight makes sense in this case, because it's not constant. So on the moon, your ISP actually is way higher in effect.
Technically, yeah, it's 6 times higher.
Right.
I mean, you can think of it that way. You can think in those terms that it's sort of 6 times higher. If you look at the way others would argue, it's like, no, you can't do that because, you know, the exhaust velocity doesn't change on the moon. It's going to be the same. Right. But as far as looking at how much propellant you would need, so as a rule of thumb, if you're trying to scale up, you know, how big of a rocket do I need to be able to do this with this ISP? It's a very easy, convenient way to be able to do it, but it only really works when you're talking about launching a rocket from the surface of the Earth.
And of course, the TLDR here is the bigger the number of seconds, the better in general. But this is where my example is going to come in. So let me do a quick share.
Basically, how good is it sipping fuel?
Yes. And let me do optimize for video. Sorry.
Now there are rockets with very, very high ISPs.
Yes. And this is what I'm going to
question is, well, why don't we use them?
Yeah. Well, this is what we're going to talk about right here.
Right.
So here we have just a really rough animation that I did. This is on the left-hand side is a Prius with a very, very small engine. And on the right-hand side is unfortunately a gray Lamborghini, but it's a very fancy car with a really big engine. So that thing, so you put the same amount of fuel in both of those. And the ISP, remember, like we're looking at how fast will you burn through this amount of fuel? Well, the Lamborghini is going to burn through this fuel, this magic number, whatever it is, in 1 second. So it's going to get a lot of thrust or power, torque, whatever it is, for 1 second going up this 5-degree hill. And the Prius, on the other hand, is only getting 1 unit of power. So it's getting 15 times less, but it's operating for 15 seconds as opposed to 1 second. And then it runs out. So we can see at this 5-degree angle that, you know, the Lambo's like, woo, I'm out of here. But then it runs out of gas. And so it just kind of slows down and eventually doesn't quite make it to the top of the hill. Whereas that Prius is kicking along because it's got a much higher ISP. And it's going and it's up the top of the hill and it's in orbit.
And it even has some extra and then a bit too much. Yes.
Yeah. So, I mean, whatever, like I said, very, very rough animation. Okay. So that was a 5-degree hill. So you're imagining a small amount of gravity. So you could imagine an ion thruster engine in orbit or something like that. Now, the difference is we have to get out of here. So now we're like on more like Earth or something, where all I've done is make this a 10-degree hill as opposed to 5 degrees.
Now we're trying to get into orbit as opposed to changing orbit.
So the angle of this hill, so just imagine, I'm just trying to make this really, really like stick with people. So imagine this is a big hill on Earth instead of a small hill. So instead of going up a little baby hill, you're going up a bigger hill now. It's a little bit shorter also just to make this work. I've got both of these. I have not changed the thrust on, or, the amount of time. So the Lamborghini is only going for 1 second. The Prius is going to go for, well, it would go for 15 seconds. You'll see what's going to happen. It doesn't matter because it doesn't get anywhere. But now the Prius like slides backwards and the Lamborghini has just enough to get into orbit. So, but exactly. So the reason why that happened, and we can just play that again, is because the thrust. So even though the ISP of that Prius is fantabulous because it will go for longer than the Lamborghini, at this point, what you actually need is just raw, in this case, torque, but you need thrust in the case of a rocket, because otherwise it just can't get off the ground. So it doesn't matter how long this thing could go for, because it's just going backwards the whole time.
And to drive home the point of using something like seconds as a measure of efficiency is that when we talk about miles per gallon, we're really talking about the entire system. We're talking about the entire car. So the fuel efficiency that a car gets has everything to do with the drag coefficient, the mass, how efficient the engine actually is, rolling resistance, your tire pressure. I mean, all these variables that kind of come in there. So if you're trying to compare two cars to each other and say, well, this one gets better miles per gallon, therefore must have a better engine, that's not necessarily the case. It may be that the other one has a far more fuel efficient engine, but everything else about it is what makes it inefficient. So if we really wanted to compare two engines to each other to find out which one is the best one. So imagine I have a 100 horsepower V8 engine and I have a 100 horsepower turbocharged straight six. So they are able to produce 100. And I decided I'm going to do this test. I'm going to call it the Gibbs test. And the Gibbs test is that I give it a certain quantity of gasoline, and maybe it's a liter. And I run that thing at full power, which is 100 horse each time. And we see how long it takes to consume that 1 liter of gas. And it may be that the V8, it's out in 200 seconds. Yet the turbocharged straight six is able to do it in 300 seconds. So therefore, we would say, based on the Gibbs scale, that engine over there is 300 seconds. The other one is 200 seconds. And it's kind of a concocted sort of thing. It's really hard for everyone to put it together. But eventually, if people understood that, they might be able to say, oh, that's how we compare a Lambo engine to a Prius or something like that, if we wanted to really get an idea of the efficiency between them. And that's what's going on with the rockets, because in many cases, we are trying to look at how good is that engine, because that might be a really good engine, but the rest of the rocket might be really bad design, which just causes all kinds of inefficiency. So if you want to compare rocket engines to rocket engines, that's what's done. And the thing to remember is the seconds is just because it's not the real units. It's the units canceling out. So again, whether you're doing SI or imperial, it's newtons per second or pounds per second. Basically, think it as force per second.
Is what it is. Again, just a little bit bizarre, but it helps a lot to think about it that way, because you're like, okay, there's nothing about seconds that's magical. It's just that we have thrust, the amount that we're kicking out the back and pushing the rocket forward, versus the amount of weight of propellant that we're using, which happens to be measured in the exact same units when you're under gravity. And then we've got per second, and then seconds just pops up. So it's like thrust per weight, basically, per amount of time, is the way to think about that. And obviously, again, assuming you don't have to get out of Earth's atmosphere or something, and then in that case, you really, really care about thrust to weight and all of that kind of stuff. But if you're in a gravity-free environment, like for an ion thruster that's up at GEO or something like that, a tiny 0.07 thrust to weight ratio is fine, because it has an ISP of thousands, so it can just go and go and go.
It's good. And up there, it only takes a little bit of a push over a long period of time to really get yourself going.
Right.
The thing is, those ion engines cannot produce really large amounts of thrust, which is what you need to be able to get something off the surface of the Earth.
In
now,
fact,
if we
they can barely
engines,
produce a microscopic amount of
right,
thrust.
right. Now, if you could scale them up to that point, they'd be so ridiculously big that it would be too massive itself to be able to lift itself.
Right.
So they just don't scale very well. That's always been the problem with like the NERVA and some of the other nuclear propulsion systems, is that they haven't really figured out how to be able to make one that has the correct thrust to weight ratio that actually could get off the surface of the Earth.
Right.
Once you don't have to worry about gravitational weight or being pulled back down and atmospheric drag and everything else, then you can change it. Everything changes. So when you talk about interplanetary kind of propulsion systems, you can talk about something other than chemical rockets.
Right.
But the only way we know right now to be able to get into orbit is we have to use chemical rockets, which seem like, paradoxically, they have the worst ISP.
Yeah.
Their ISP is horrible, but they're the Lambo. They've got so much horsepower. It doesn't matter. Just give them, a big tank of gas and it'll get you there. Right. But, the Prius, if you go uphill, it doesn't matter. You just don't have enough pop. You can put as much gasoline as you want in there, but if it can't produce the horsepower, it's not going to go anywhere.
Right. And I think that's the really, really critical part here, is that I think people get really confused because Earth is a special case. If we were launching these rockets from out in the middle of nowhere, just, in some orbit around the sun, we would care only about ISP. We would say, sure, it doesn't matter if it takes a month for it to accelerate, but it's going to get to a fifth the speed of light or something in a month. It's like, well, that's great. You can't do that with a chemical rocket because it burns too much propellant, excuse me. But on Earth, we're stuck in a gravity well, which means we need a whole crap ton of thrust to get out of the gravity well. And then we can use a different propulsion system once we're out of the gravity well. Yeah.
Yeah. So John, I'm glad you corrected yourself with the fuel and propellant.
Yeah.
Because, it's like that in the Roomba with me, that if you get that wrong, I get a little bit upset there. But yes, it's propellant, it's reaction mass. That's what makes the rockets move forward.
Right. Yes. And again, just for people who might not know, that the fuel would be like, that's the gas in your car, right? That's fuel. And that's correct. But what you get for free out of the Earth's atmosphere is you get oxygen, but you don't get that in a rocket. So you have to put that in a tank and you have to cool it down, generally speaking. And that's the other half of the propellant. So you can have RP1, which is just basically fancy gasoline, but then 2/3 of that propellant mass is actually oxygen in that case. Because
and RP1 literally is fancy gasoline.
Yeah.
It's just highly refined kerosene to the level that they need for a rocket engine. And even though we need the oxidizer to burn the fuel, one of the benefits of it is it's also a reaction mass. So when it goes out the rear as the exhaust, it's the reaction mass. And this is what's it's one of those things where the actual byproduct of the combustion, which you never want in anything else, which is exhaust. And every other thing, whenever we burn something, we're always trying to get rid of the exhaust. The exhaust is the actual product that we want. It's the one time we want it. So we don't care about the fact that there's the oxygen is going in there and the fuel mixture and everything else. The more mass we can put in there, the absolute better. Right. And that's the serendipity of why a rocket is able to work. And this goes a little off topic. And if people want us to do a full episode on this, we can, but it is worth touching on what the reaction mass matters. That hydrogen and oxygen is the best that we know of for chemical reactions, because hydrogen is so light that it's incredibly energetic. The particles of O2 that come spitting out the back end of the rocket engine are moving really, really fast because they're super light, which means that you get a better ISP with something like the space shuttle main engines. But you notice the space shuttle also had to have 2 solid rocket boosters because it didn't have the thrust. So, it had great the tanks
ISP.
Have to be really, really big.
Yeah, and I mean, hydrogen is its own. It's just a
volumetrically, it's terrible. If you look at it from other metrics, it's great, but as soon as you realize how big your tanks are, it starts to lose its efficiency.
Yeah.
Really
and hydrogen, because it's the smallest molecule, also can escape very easily. So it's really hard to keep it trapped.
Yeah, the weld qualities and everything you have to have, or something else, and your seals, as we know from Artemis, become a bit of a problem. And that's the other thing with the ion engines, is that when you start talking about what is the best, it's not just the amount of mass that you have, it's the type of mass. So the heavier the element that you're spitting out the end, the better. So argon is not the best one to use.
Right.
Neither is krypton. It's xenon. I mean, you could even go up higher, but at some point you're talking about unobtainium. But for if you're going to be using ion propulsion, the ideal one based on cost and availability and a lot of other things is kind of xenon. You really want to go there, but it turns out it's not quite as available as you want. So you go down to krypton, and it turns out it's still not quite as available as you want for the full need. So you go down to argon, but you could, in theory, use probably hydrogen in an ion propulsion engine, but it would have horrible ISP. It just doesn't work. So
yeah,
that's one of those things. It could be a long episode to explain why that is.
Yeah. And it really comes down to, in a chemical reaction, hydrogen's great. In something that's more of an electrical, it's a linear accelerator, basically. You want something heavy to react.
You want more. There's some simple math behind it, and it has to do with just momentum. It's like in the end, you're taking two things, you're able to put the same amount of energy in them. So in the end, I've got a light thing and I got a heavy thing, and both of them end up having the same kinetic energy going out. So you think, well, if they have the same kinetic energy, it must have the same push. It's like, oh, nope. Because momentum is not 1/2 mv squared. Momentum is mv. And when you kind of work out what the momentum is for that same kinetic energy, it turns out you get way more momentum for that heavier one, even though it's moving slower. It's moving a lot slower than the other one. So at first it seems paradoxical, but the faster moving one should be better. It's like, turns out it's not for the ion propulsion engine. And it goes as a function of the square root of the mass ratios.
Right.
And considering argon is like 28 or something like that, and hydrogen is 1. Yeah, you can see there's a big, or is it 28 or I have to remember. I'm probably wrong in that, but it's up there. It's oxygen is 16, argon's after that. So for some reason, I'm thinking 28, but it's
and then especially when you get difference. Like xenon, and by the way,
xenon gets a lot higher. Xenon, I think, is 100 something.
The far right of the periodic table, which is the noble gases, because their outer electron shells are filled. And that means that they're really, really good to store. But what you have to do is knock an electron off before you accelerate them so that they become electrified. Anyway, we can get into all of that stuff at a later point, but hopefully this one at least helps to give you a bit of a gut understanding of what ISP is. I think that's the problem, is that people are like, I just don't know. And I have to admit to even, it's taken me a long time to get sort of a gut feeling of what it is. And I finally
so argon is 40 for atomic mass, and that's what's important. Its atomic number is 18. Right. Its atomic mass is 40. So you're really talking about it being 40 times more massive. Take the square root of that. That's how many times more efficient it is as a mass ratio when you compare it to hydrogen. Right. So what's the square root of that going to be? It's going to be at least 6 or something like that. A little bit more than that.
Six and something. So
take the closest square I can think of is 36, right? So it's pretty close to it. So somewhere around there.
Yeah, 6.3 maybe, something like that. Yeah. Anyway, so good. Hopefully this helps people. Definitely let us know in the comments if you have other questions, and if you want us to do a whole one on chemical versus nuclear versus like ion type engines and things like that, and what the differences are and what the specific use cases you would want to use them for would be great, because that's a lot of fun to talk about. I mean, talk about geeking out. We can do that all day. All right. Again, thank you so much, Scott. I know you're laughing. You're like, hell yeah, do that. Thank you so much for being here and for doing 2 videos in a row. And if you didn't see the other one yet, definitely watch the first one so you can catch that. So again, Scott, thank you so much for being with us. I really do appreciate it.